Welcome to this explainer. Today, we're doing something a little bit different. We are jumping right into a highly practical workstation demonstration, engineered specifically for critical care doctors. We're going to dive right into exactly how you can safely, rigorously, and effectively integrate AI into your medical research pipeline. We are definitely not just talking theory here either. We're going to use a grounded, real-world clinical scenario, specifically sepsis-associated acute kidney injury, or SAAKI, to show you exactly how this entire workflow functions from start to finish.
Okay, let's take a quick look at our roadmap for today. We'll be pushing that SAIC clinical scenario through 6 distinct stages: the AI research paradigm, formulating clinical questions, advanced literature mapping, protocol design and analytics, academic integrity and writing, and finally, the final publication strategy. Let's get to it.
This quote right here really hits the nail on the head. It perfectly highlights our core paradigm shift. I want to be absolutely clear right out of the gate. AI is not some magic button that lets you bypass critical thinking. If you treat it like a casual chat engine, you're going to get unscientific results. Simple as that. Instead, we really need to view AI as a virtual team of highly specialized collaborators. Moving into Section 1, the AI research paradigm, ground rules and boundaries. Let's quickly establish exactly where AI accelerates your work and where your clinical judgment absolutely has to stay in the driver's seat. So this comparison perfectly captures the RAISE 2026 standards. Think of it this way. You let the generative models handle the heavy lifting for administrative and stylistic tasks. I'm talking about literature matrix synthesis, data formatting, syntax polishing, and structuring those tedious citations. But on the flip side, human investigators retain complete ownership of the raw datasets, the study protocol design, the clinical heterogeneity adjustments, and of course the definitive conclusions. You are the pilot, AI is just the engine.
All right, Section 2, formulating clinical questions. Here, we're moving from vague ideas to highly structured instructions. Before you type a single word into these tools, you've got to use the AIM framework. That's A-I-M. First, tell the AI its actor role. Who does it need to be? Maybe a senior critical care biostatistician? Then, provide the input. What specific variables or custom clinical data is it actually working with? And finally, declare the mission, the definitive single task it needs to execute for you right now. Let's actually look at how this builds a real PICO matrix for our urinary NGA and sepsis study. Look at the stark difference between the AI's initial draft and the human correction here. The AI just gives a super generic population, sepsis patients. But then, the critical care expert swoops in to enforce strict clinical definitions, changing it to adult septic shock patients. The AI says the outcome is to predict AKI, but the human corrects it to Katie Geigo stage 2/3 SAAKI development and 30-day ICU mortality. This perfectly captures that human-in-the-loop rhythm. You draft with AI, sure, but you finalize with real clinical expertise. Which brings us to Section 3, advanced literature mapping. We need to go way beyond flat keywords so we don't accidentally miss regional or negative result evidence. Look, if you're relying purely on flat keywords, you are missing critical data, for sure. To build truly reproducible search strings, you absolutely must combine controlled vocabulary, like mesh, with the advanced syntaxes shown right here. Notice how using an asterisk for diabet catches all the lexical roots, diabetes, diabetic, diabetics, or using a wildcard question mark in woman catches spelling variations. This is exactly how you ensure your net is cast wide enough to capture all the relevant evidence globally. And this right here is where things get really exciting. Modern semantic tools are total game changers. Interactive node graphs like this one from Connected Papers literally map the literature visually based on co-citation, generating these semantic discovery clusters. It helps you instantly spot seminal papers you might have completely overlooked. But a massive word of caution here. AI often relies heavily on highly cited Western abstracts. You must always manually inject local registries like CTRI or InMed in India into your reference manager to prevent severe geographical publication bias. Okay, let's jump into Section 4, protocol design and analytics. This is where AI workspaces become incredibly powerful, but honestly, highly dangerous if left unsupervised. When you start using advanced tools like Claude to synthesize a prospective cohort methodology, you have to upgrade from that AIM framework we talked about earlier to the core framework. You establish the context of the medical domain, state the single objective, assign the expert role, and, most importantly, set rigid expectations. You absolutely have to give the AI explicit boundaries so it doesn't just hallucinate your lab procedures or totally forget to exclude patients with pre-existing severe chronic kidney disease. Here's a fantastic example of an AI analytical workspace directly in action, parsing a raw Excel dataset. The AI executes a data validation plan, easily checking data distributions for non-normal boundaries. This is brilliant because it acts as an immediate alert, guiding you to select safer non-parametric statistical tests, like the Mann-Whitney U, rather than forcing inappropriate parametric models onto your data.
But, and this is a massive but, beware of the AI's analytical blind spots. If an engine spits out a perfect 1.0 ROC or AUC score on your logistic regression, it might look like a huge triumph at first glance. But as a human expert, you must recognize that in clinical data, absolute perfection almost always implies critical data leakage. The AI might have accidentally included post-AKI creatinine data as a baseline predictor. It's completely up to you to manually isolate that faulty predictor and adjust the covariance. Remember, AI calculates, humans validate.
Moving on to Section 5, Academic Integrity in Writing, or as I like to call it, purging the AI fingerprints. Once our stats are locked in, we need strict constraints to actually write the manuscript. We've all seen it. Standard AI output looks incredibly polished, but it's often completely hollow. It loves to discuss the importance and implications of things without citing any exact studies or real numerical results. To fix this, you must command the AI to write using only the specific literature citation files you upload to the workspace. If you don't anchor it to real NBIB or RIS files, it's just going to generate sweeping, generalized claims, totally devoid of scientific evidence. When you're reviewing those AI drafts, you absolutely need to be hunting for these massive red flags. Actively purge generic filler language, stuff like, in today's rapidly evolving world. Watch out for artificially complete answers that lack nuance, or those excessively robotic transitions like furthermore and moreover. But most importantly, be highly vigilant against tortured phrases. This happens when an AI tries to outsmart plagiarism checkers by blindly swapping jargon, turning a serious, standardized term like acute kidney injury into something utterly ridiculous like abrupt renal harm. To catch all this before you submit, you really should run your manuscript through specialized scholarly pre-flight assistants like Trinka AI or PaperPal. These tools are engineered specifically for academic prose. They allow you to verify your text against duplicated wording, check reference validity, and ensure your grammar is pristine. This is also exactly where you ensure you've included your mandatory Prisma Trace transparency disclosures, explicitly stating exactly how AI was used in your methodology. Finally, we hit Section 6, the final publication strategy. We are at the finish line, optimizing for high-impact journal submission. Major journals today basically expect a graphical abstract to accompany your text. The gold standard is a strict 3-column visual rule: study population, main exposure, and associated outcomes. Now, using dedicated scientific vector libraries in platforms like BioRender or Mind the Graph, you can build these really easily. You honestly don't need any background in graphic design to create scientifically accurate, beautiful, publication-ready visuals. Now, to prevent those frustrating instant desk rejections, please don't just guess where to submit. Always input your manuscript title, abstract, and scope into automated publisher portals, like the Elsevier Journal Finder or the Springer Journal Suggester. These algorithmic engines will match your work with the most strategically sound journals, ensuring your rigorous research actually finds the exact right audience. As we wrap up this workstation demonstration, honestly, you might want to screen grab this checklist or just print it out for your desk. Before you submit anything, ensure you've structured your Pico pillars before prompting. Verify you've mixed your search syntax and checked regional registries for complete data coverage. Audit those statistical models for data leakage, run a strict integrity scan for tortured phrases, and always include your AI transparency disclosure. And a golden rule: never accept an AI citation without actually clicking the original DOI. AI is an absolute powerhouse, but only when it's driven by your specific clinical expertise. It removes all that administrative friction so you can actually focus on the science. So the only question left for you as we close out this explainer is, how will you step into the driver's seat and leverage these tools for your next big research breakthrough? Thank you so much for joining this demonstration, and we'll see you next time.